Welcome back to Rates of Reaction Lesson 9. This is equilibrium. So the AQA specification links are there if you want to look those up for more details. Students at the school where I teach, these are the resources we've got available in these lessons, and the book references are there on the left hand side to help you if you're accessing these books at home. Okay, I like to start every lesson with a little bit of a picture quiz. So here we are. If you're watching the video version, you know already what the lesson title is, but those of you that don't, or you've just come into this a little bit later, then see if you can work out what the lesson title is. Alright, so first of all we've got the E, okay, an E there for the brand EE, and then a quill. A quill, very old-fashioned, one of the first writing implements. Okay, a feather where they dip it in ink and use the ink and the end of the feather to write. IB, okay, the symbol there for the International Baccalaureate. Okay, an equivalent, an alternative to GCSE. Then we've got brie, cheese, and then there's a gentleman on the end who seems to be saying Okay, so if we put all those together, we get equilibrium. Right, the AQA specification, this is what it says about equilibrium, what the students should be aware of. Other exam boards, you may have other things that you need to consider. So do check, if you're not with AQA, if you do check with your exam board specification, just to make sure that everything is covered. Learning outcomes for the lesson, if you want to read through those in more detail, just pause the video now. Right, we've got two images here, and there's a difference between them. The difference is fairly obvious in terms of the apparatus, and we're setting it up as if it's a reversible reaction. So A plus B reacts to give us C and D. So if the products C and D of this reversible reaction were gases, what would happen in image 1? Yeah, the gases would escape out of the top. Okay, so they wouldn't actually be available still in order to react back into A and B. By using a bung, so in image 2 we've got a bung in the top there, we actually create a closed system which prevents anything from coming in, and it also prevents the gases from leaving. Okay, so what would a definition for a closed system be? Good, hopefully you've come up with a statement, a definition similar to what we've got here. So a closed system is a system in which no matter enters or leaves. It's sealed, right? And so by sealing in image 2, what we've done, we've kept our product C and D in there, and so then that would be able to react again to make A and B. Okay, so that's what a sealed system is, or a closed system. Okay, that's the term the exam board will use. They will say a closed system. So if we had a closed system, so think back to that bung on the top, if we had a closed system, what would happen to the rate of reaction for the forward and reverse reactions in a closed system? So we've got A and B, that's going to be your reactants, and they will then react to form C and D, your products. So in a closed system, we need to think about how the rate's dependent on the frequency of those collisions and the concentration of the particles. That's also going to affect the rate, because that will affect how frequently they collide. Okay, so just think about initially what the concentrations of A and B would be and what the concentrations of C and D would be. All right. So here's what would happen. Now, there's a lot of writing here, so just want you to listen carefully to start with. In a reaction between A and B, creating C and D, in our closed system, it's a reversible reaction, the reactants A and B, that's all you would have at the start. Okay, and so there'd be a high rate of reaction for our forwards reaction because we've got a high concentration of A and B. We've got frequent collisions between A and B. At the very start, our backward reaction with C and D, because we haven't made C and D yet, the concentration of C and D is 0, so there would be no backward reaction at the start. As C and D begin to be formed, okay, they would then start to react again at a low rate of reaction because the concentration is very low initially, so the frequency of collisions won't be often. So there would be a low rate of reaction for the backward reaction. So that's point number 3 there. So as the rate of the forward reaction is currently much greater than the backward reaction, okay, because we've still got lots of A and B, so the rate of our forward reaction is still going to be greater than the backward reaction. But as A and B are reacting, they're forming more C and D. So C and D starts to build up. The concentration of C and D is getting much higher. So therefore the rate of the backward reaction will increase. So as A and B are getting used up, the rate of the forward reaction starts to slow down. And C and D are getting used up, so that starts to slow down. And eventually we reach a point where the rate of reaction for A and B is the same as the rate of reaction for C and D. And this is where we reach our equilibrium. So what I want you to do is I want you to try and use those statements. I want you to set up a graph of time on your x-axis and then the rate of reaction on your y-axis. Alright, so just remember that A and B, we're starting with a high concentration, so there's going to be a high rate of reaction to start with, and then C and D, there's virtually nothing to start with, so there'll be a 0 rate of reaction to start with, but then that'll gradually come up as A and B gets converted into C and D. It's quite a difficult task, this, okay, it requires you to think a little bit about this, but have a go at doing that now. Well done if you've got a graph similar to the one I'm showing you. It was a difficult task to do, and what you should have is you should have your line for A and B is going from the top left corner and it's slowly curving down and then flattening out in the middle of the page. Then your line for C and D is coming up from the bottom left corner and then slowly flattening out in the middle of the page again. So what we'll do is we're going to link the statements 1 to 7 on the left there. We'll link them to the graph so you can see what we're actually describing there. If you haven't got a copy of this, then make sure you draw out a copy now, please, and then you can actually make these notes as we go along. So at point number 1, this is when we've just got A and B at the start, so the rate of reaction for A and B is very high. Okay, so that's why the line starts up there. Number 2, there is no C and D at the moment, so there's 0 rate of reaction for our backward reaction there. As C and D start to form, we begin to get a low rate of reaction for that backwards reaction. Okay, so we're getting some C and D, so they can then react together to form the A and B again. The rate of the forward reaction is still much higher than that of the backward reaction. So C and D are starting to build up quite a bit now, so the rate of their backward reaction is now much higher as it approaches that equilibrium. A and B are being used up even more now, so the rate of their reaction starts to slow down. And then ultimately both reactions slow down to reach a point of equilibrium where they're at the same rate. So you might want to watch through that slide again there, because that was quite complicated. So do go back and re-watch that if you need to. But based on what we've just seen, can you come up with a definition for equilibrium in terms of the rate of reaction and linking that to the forward and the backwards reactions? Excellent. The rate of the forward reaction is equal to the rate of the backward reaction. That is what equilibrium is. It's when the rate of the forward and backward reactions are equal. So why do we sometimes call it dynamic equilibrium? This is a term, dynamic equilibrium, that you may well read in other textbooks or hear on other videos. So whilst the rates of the forward and backward reaction are the same, this is our equilibrium, the reaction doesn't stop. It is still going on. Okay, so A and B is still being converted to C and D is still being converted to A and B. But because they're happening at the same rate, okay, it doesn't look like anything's happening. So the equilibrium is the same rate, and the fact that it's still stuff going on, there's still reactions happening all the time, is why it's dynamic. And it's sometimes, an escalator is sometimes used as an example of this. So the escalator's moving down and that the man's running up, yet it appears like he stood still. Okay, so the man and the escalator have reached a state of dynamic equilibrium. They're moving at the same rate, and so he's staying still, but there's still a lot of work being going on to stay in that position. All right, do go back to those slides, because this is a very complicated lesson. So do go back to those slides and listen through those again if you need to. We're going to look at what happens to the concentration of reactants and products of a reversible reaction in a closed system. Okay, so again, we're looking at starting with A and B and then seeing where the reaction goes. So what I want you to do is to come up with what you think the concentrations of A and B and C and D would be at various points of our reversible reaction that's in a closed system. Right, the chances are you've probably come up with something similar to what I've got there on the left, okay, where the concentration of reactants and products are equal at equilibrium. So you started with A and B being very high and C and D being very low. Okay, that's spot on. And then halfway you've assumed that A and B would be high, C and D would be low, and then at equilibrium you're saying that both of them would be a medium concentration. Is this correct? Right, we're assuming in our reaction mixture that the concentration is going to be 50-50. Okay, sometimes at equilibrium the concentration of reactants and products might be 50-50, but it is possible to have cases where the ratio between those might be 60-40 or 70-30. So remember, at equilibrium the rate of the forward and backward reaction is the same, but that doesn't mean the concentration of reactants and products is the same. Okay, equilibrium is all about the rate being the same. So we're going to look at a couple of examples now. So here we are. Here we've got a concentration time graph for a reaction of A and B and C and D. Okay, so what I want you to do is describe what happens to the concentration of reactants and products of this particular reaction in a closed system. Right, at the start, A and B we have a high concentration, C and D low concentration. About halfway through our reaction is when they have a similar concentration, where those lines cross. Okay, and then at equilibrium, when the rate of the forward reaction is the same as the rate of the backward reaction, they both A and B have a low concentration or a lower concentration, and C and D actually have a higher concentration. So this is an example here of showing you that the closed system has reached a state of equilibrium, but that doesn't mean that the concentration of reactants and products is equal. It's just the rate of the forward and backward reaction. Right, another example here. Okay, we've got an example to show at the bottom there. So on the left hand side, you've got the concentration graph and time, and then on the right hand side you've got the rate graph and time. And whilst it's a bit more complicated than usual, the K N2O4, that just means the concentration, and the KNO2, that's just the concentration. Okay, so you can see that when we look at the concentration graph on the left, the NO2 starts off at 0 and then goes up, and whereas the N2O4 starts off high up and then comes down. So where the equilibrium is achieved, where the rate of the forward and backward reaction is the same, as you can see in the second graph, at that point the concentrations of the two things are not the same. So this is another good example that we can use later on when we look at altering conditions, because with the gases involved, the gases have different colours. And so you can see early on in the reaction you have this kind of slightly pale bluey grey kind of colour, and then it becomes more of a yellowy colour midway through, and then a brown colour once equilibrium is reached. And that's with reversible reactions, you can see some of the changes in terms of concentrations with these colour changes. And we'll look at that more when we look at altering conditions in the next lesson. Right, we've been talking about equilibrium being reached by starting with A and B, ending up with C and D. It can be reached in either direction, so we could have started with C and D and ended up with A and B. So these graphs here, they just show that in a bit more detail. So the first graph is when your SO3 has started off at very low concentration and then built up. And then on the second graph, the SO3 started with a high concentration and come down. But in the second graph, the SO2 and the O2 have started at a 0 concentration and gone up, whereas in the first graph, they started at a higher concentration and came down. All we're doing here, these are just examples of, instead of going from A plus B to C and D, we've just flipped it, so we've gone from C plus D to A plus B. That's all this is. It looks complicated, but that's all that's happened. Okay, there's another one to look at too. So here we've got our NO2 and our N2O4 again, and the one on the left, the NO2 starting at zero concentration, but the N2O4 is starting higher up. And then on the right, the NO2 is starting higher up, and the N2O4 is starting at 0 concentration. And either way, you can see how the point of equilibrium that they reach is the same. Okay, the concentrations of those two chemicals is the same equilibrium, whichever direction you come at it from. So this is the Haber process that you'll learn more about in the altering conditions and resources topics. So again, same thing. We've just got a reaction, and we're just showing the two different directions. At equilibrium, you can see the concentration of all of those substances, hydrogen, ammonia, and nitrogen, is the same, whichever direction the reaction goes. So in the first one, on the left there, A, you've started with hydrogen and nitrogen, high concentration of them, and you've had 0 ammonia, and then as the hydrogen and nitrogen have come down, the ammonia's gone up. On the other diagram, B, you started with a high concentration of ammonia and 0 concentration of hydrogen and nitrogen, and as the ammonia has come down, the hydrogen and nitrogen have gone up. So you can see it's the same. The equilibrium mixture is the same whichever direction the reaction goes. So this leads us on to altering conditions and starting to think about how we can get our best yield. Okay, so reversible reactions are used a lot in industrial processes. It makes economic sense to get as much of your product as possible, the highest yield possible. So companies, they try and alter conditions in order to get the maximum yield they possibly can. So what sort of things could they change in terms of their reaction in order to get the maximum yield they possibly could? Good, they change conditions. So they change the temperature, they change the pressure, they change the concentration, and they also might add in a catalyst. Okay, it's not just as simple as changing the conditions, however, because they do have to consider the economic impact of doing that and safety impacts as well. Okay, because altering conditions can make reactions more violent. Okay, some of the pressures they use are extremely high, so we do have to consider other things and also the cost involved in doing those. Finally, Le Chatelier's principle. So this is a principle you need to know in terms of what happens when we alter conditions. Okay, I'm bringing it in now just so you know it before we go on to the altering conditions lessons. You will use it a lot in the next lesson, but I think it's best to introduce it now. So Le Chatelier says that whenever a change in conditions is introduced to a system at equilibrium, so when the rate of our forward and backward reaction is the same, the position of equilibrium shifts to cancel out the change. Now then, to a lot of us, that'll just be make no sense at all. All right, that this idea of the position of equilibrium. But the position of equilibrium is just the way of indicating which reaction is in our reverse reaction is dominant. So which one we're getting more of. Okay, so I'll show you some examples now. So if we said the position of equilibrium shifts to the right, then what that means is it's favoring that forward reaction. Okay, so you get more product. Okay, remember our products are on the right. If we said the position of equilibrium shifts to the left, then that means it favors the backwards reaction. Okay, and we get more reactants because remember our reactants are on the left. So saying that the position of equilibrium shifts to the right just means we get more product, and saying that the position of equilibrium shifts to the left means we get more reactants. This is just some of the language that you'll need to get familiar with. This is similar to when we talk about reversible reactions. Okay, next lesson we're going to be looking at altering conditions and why changing some of the conditions can actually give a reversible reaction, a better yield for a reversible reaction, because that's particularly important in industry. Thanks for watching, folks. I'll see you next time for our lesson on altering conditions.